Okay guys, mga sangkay, good afternoon. I'm going to have a tutorial of this two-way slab. Again, this is based from the design standard from British Standard 8110 or BS 8110. Okay, so in the design of two-way slab, uh, take note that we need to have the coefficients. Okay, these are the coefficients that we need from the table. This n is the combined loads, and take note, if you have a x stands for a short span and y stand for a long span. So if this is x, it is also x here. Okay, so this is the moment that you are going to get from along the short span, and this is the moment that you will get along the long span, which is y. X is short span, and then also here you have also long span. Okay, so n, as I said, this is the load combinations 1.4 and 1.6 according to the BS standard, or British standard I should say. Then we also have the table that we are going to use for our shear. Okay, VSX along long span, and then VSY along VSY along long span, and VSX along short span. So these are the coefficients that also we are going to get in the table. So this is LX and LX. Take note, we don't consider here long span, only short direction. Okay, so this is what I was saying earlier, that this is the moment along X and this is the moment along Y. Okay, this is long span, and then this is short span. Okay, so this is the value of your coefficients for your moment. So for interior panels, let us say you have here, okay, these are the slab. So okay, for example, this is the slab. There's a slab here, slab also here. So this one is the interior panel. Okay, so how about this part? This part, you have here two adjacent discontinuous. Okay, discontinuous here and discontinuous here. One long edge discontinuous, maybe only this one. Okay, only this side. Okay, so this one is one long edge discontinuous. There are only three, okay, type of panel here in the British standard. So just have to look among these types which fit well to the slabs that you are going to design. Of course, this is the ratio. For example, Ly for this is 4, and then this is 4 over 4 becomes 1. So this is the value of your ratio. And for long span coefficients, there is no need for the ratio. Okay, this is for all values of the all values of the ratio. So it only considers ratio along with the short span. Take note, this is for coefficients for your moment in the calculation of the two-way slab. Okay, let's move on to the next slide. So this one, again, you still have here this ratio, and then similarly for the type of panel, you have 4 edge continuous, meaning it's interior panel, and then one long edge discontinuous, and then two adjacent edges discontinuous. Okay, so values, you have X and then Y. Okay, so these are the coefficients that you're going to get. Okay, this is just in the continuous edge. Okay, because shear is only located at this support. Okay, there's no shear in the midspan. Okay, so for example, this one, again, in the design procedure, you're going to look at what would be your imposed load. Okay, this one, what would be the imposed load that you are going to use coming from the table. Okay, you have to check your table. What is the type of like occupancy, if this is a bedroom or that's hallway or whatsoever. Okay, and then of course you might have additional consideration for your selling load, and then your FY, it's up to you to choose. Okay, if that's 500, and then concrete cover usually use of 25. Okay, so now the thickness of the floor here, based from what you have learned in one-way slab, you can just use that method to come up with the assumption. In this case, we assume already 180. If you already have your expert judgment, meaning you have already experience in the design, then you can just come up right away with your assumption on the particular thickness that you are going to use for your design of the slab. Okay, so let's continue. So for example, You have here, okay. First, you are going to calculate the dead load. As I said, you know it already how you're going to calculate the dead load. This one is for your finishes. This one is the thickness of your slab. And this one is your unit weight of concrete, 24 kilonewton per cubic meter. Then you have the combination, the imposed load or live load, which is coming from your table. Okay, if it's bedroom, hallway, or whatsoever. And this is of course your combinations, and this is the formula for your moment. This is the components that coefficients that you're going to take from the table. Okay, for example, AB23, panel AB23, where is that one? A, B, and then 2, 3, meaning one edge is discontinuous. So what is that? Where's that one? One edge. This one. Okay, and then take note that the Ly over Lx is 7 over 5 or 1.4, meaning you have this one, 1.4. Okay, for coefficient, okay, along x or along short span, the negative moment coefficient is 0.068. Positive moment here, meaning positive moment mid span. Okay, negative moment meaning at the support. But for long span, you have here at the support negative moment and positive moment. Okay, there's no corresponding ratio of your Ly and then Lx. That's why you have these values, 0.051 and 0.028. So from it, this one you can use already. 0.051, you use it here. This is the moment that you're going to use for your short span. Okay, coefficient. Okay, Sx. Okay, Lx 5. 5 is the short span. Okay, so squared. Here, take note that this one should be y, okay, because we are considering here long span. The book has its like some kind of mistake, okay. So this is 7 squared. This is the coefficient that you take from the table. Long span is 0.028, okay. This is the one, okay. 0.028 long span, okay. Short span is 0.051 for positive moment, okay. Mid span. Okay, now for example BC12, where's BC? BC12. So two edges are discontinuous. So this is the one, okay? Here. Okay, negative moment. In this case, you take ratio and proportion because your ratio of your long span over short span is 1.87. So this is somewhere here, okay? So you can have 2 minus 1.75. This is the one, okay? The value of 2 is 0.07. That is, we are talking about positive moment, okay? Positive moment, meaning it is at the mid span, okay? So 0.07, and then this one is 0.065. Now we would like to know this 1.87 corresponding value for 1.87, okay? And then this 1.75, and then this value we don't know yet. That's why I write here x, and then 0.065 is this one. So that's how we are going to get the value of 0.0675, okay. But of course, in the design, this is 0.0675, okay. 0.034 in the long span is not a problem, okay, because there is no specific ratio for Ly over Lx. These values are could be used for all the ratios, so you just have to copy. You only have here 1.034. Only that you're going to identify the values for short span. But for conservative design, and then to avoid you for a difficult task, maybe you would like just to use 0.07, a matter of 0.0 something, okay. I think it doesn't, it makes sense that you can just use this 1.07 without having interpolation, okay. So for example, BC23, BC23, so this is in the interior part, okay. So we go back here, interior, okay, negative meaning at the support, positive meaning at the midspan. So this is the ratio that we take between long and short span. This is the coefficient at the negative moment, meaning at the support, coefficient at the positive moment, maybe meaning at the midspan, okay, for short span direction. For long span direction, again, there's no specific values for each ratio, so it's okay, it's fine, okay. So now we take these values, 0.05, 0.037, 0.32, 0.24. It's from the table. You can check it by yourself, okay. Negative moment here, meaning at the support, okay. Positive moment at the midspan, you substitute here. Short span meaning use 5, okay. Short span use 5. This one we calculated already earlier with the combination. Long span, this is 7. Okay, this is 7. And then these are the values that we have here. Okay, 0.032, meaning negative moment. Okay, at the support. Mid span is positive moment, so you have here. So we are going to use these values. Okay, for example, short span, mid span. This is mid span, and then mid span. You are going to have these values, and then here. At the support here and then here, we choose which is bigger. The bigger will be the main reinforcement, the smaller will be the secondary. Okay, so this is the table again that you're going to use. Okay, let's design at the support, meaning negative moment support. These values we take from there. Okay, and the coefficients that we had in computing the moment. Take note that at the support, the reinforcement is at the top. Okay, so the total here is h, so you have here h minus diameter of our reinforcement is actually 10. This one is 10. Okay, so you have here 10, so 10 over 2, and then minus c, 25. C is here. Okay, now for the secondary, okay, that one secondary, this is the secondary reinforcement. Okay, up to here you have h, you just subtract another 10, and then 10 over 2, and then the concrete cover, which is 25. That's why your secondary is just 10 millimeter smaller than the distance of the main bar. Okay, so we use the formula. This is just the formula for the main reinforcement. You use the bigger moment. Okay, you have here the FCU that you use, 20 megapascal. Take note that this is Newton, this is Newton millimeter squared. All units are in Newton and millimeter. This is 1000 millimeter, or 10 to the power of 3. It's the same. Okay, and this one is 150 millimeter, our effective depth. This is unitless, okay, because this is just the K constant. D is 155. Oh no, 150, we substitute it, and then K we already have here. So this is our value, but we have to compare it with the point. This is the value, I should say. Compare with point. Okay, 95D. This is 95D. 0.95D. So between the two, you are just going to use the smaller value. So in other words, here your value is smaller, is 142.5. Okay, this one is 142.5. These values, or this one, is equal to 144. Okay, 144. Okay, 150, and this one is 0.96. Total is 0.96. 144, 142.5, you are going to use the smaller value. So this is actually, this one is 142.5. So your AAS is 359.26. The minimum value is 234 only. How are you going to solve this one? 30%, meaning divide 100. 0013. B is 1000. H is, this is our H, 180. Okay, you check in the first slide. So our requirement is 359. We can use this one. This will provide 359. So spacing is 200, and then you have 10 millimeter is your size. Okay, so this one is your for main bar. Secondary, you use the smaller value. Okay, smaller moment. So the same procedure, you have 0.03 here, and then you compare again. 0.95 of 140 is 133. This one is equal to 135.8. So between the two, you're going to use the smaller one. Okay, that's 0.95 of 140 or 133. You can have this requirement of your area reinforcement for your secondary bar. This is along the long span direction. So the minimum is 234, so it's fine. We're going to use this one. Look at the table. We need 307. 314 is enough. Okay, so the spacing is 10 and 250. Okay, 10 and 250. No, this one. Okay, so we go to the mid span. So the mid span, actually the reinforcement just located in the bottom. Okay, in the bottom you have here, this one is secondary, this one is the main reinforcement. This is the moments, these are the moments, I should say, that we have calculated earlier. Okay, the distances, this is 150, 140, it's the same. This main bar as 150, again here like that. Here is 150, okay, or D. Secondary bar, this one, from here it's 140, okay. The difference of them is only 10. Okay, the same concept that we had in our previous calculation. So we calculate reinforcement AS for main steel. We use the bigger one. The smaller one will be the secondary. The same calculation you have here as your requirement, and then this one is the this one is the minimum. So therefore we use this okay, this is minimum, so it's fine to use this one. We need 269. We can provide with 314. That's why here, okay, take note here, 314 has a spacing of 250. No, here 250. Okay, so you have here 10 at 250. The area that is being provided is 314. What we need is only 269, so it's fine. Okay, now secondary steel, our calculated area is 226. The minimum is 234, meaning we need to use this 234 because that's the minimum value. 234, we can use 262, meaning 10 millimeter and 300 mm spacing. So you have here, no, here 10 and then 300. This is the provided area. 262, what we need is 234, so everything is fine here. Okay, so the shear, and our shear, we know that our ratio is 1.4, and then along Y we can use 0.33, along X we use 0.43. So we just use that one. Okay, for our shear at along Y direction, BVY, we have 0.33, and then this one is 0.43. For X we use just the same, okay, 5, the short span. This is the combined load, combined moment, combined load. The actual shear stress, this is V, this is the, okay, the critical one that we are going to use. B is 1000. Take note, this is Newton, this is millimeter, and this is also millimeter. 10 to the power 3 is 1000. So this is the actual shear stress. Okay, we need what would be our allowable. So for our allowable, we have to, okay, calculate this one. Okay, what is 100 AS over BD if our AS is 393? So we can use this value as 0.26. 0.26 is where it's here, okay, here. Okay, so we need to interpolate to get 0.52. Okay, we have these values of how are you going to interpolate. Okay, 0.5 and 0.25 was that one, 0.5 and 0.25, because 0.26 is between 0.5 and 0.25. The corresponding value 0.5 is 0.64, and then this one is 0.51. So 0.64, 0.51, and then we'd like to know the 0.26. Okay, minus 0.25. 0.25 is here, the limit, here. Okay, okay, okay. So you have X. We need to get the corresponding value of that 0.26, so we write here X and then 0.51. So therefore we can use 0.52. 0.52 is somewhere here in between just 0.64 and 0.51. That's correct, because our 100 AS over B, this 0.26 is over here. Okay, so you use this 0.52 here. We need to multiply by 30 because this is our FCU that we used. According to the code, we get the proportion of 30 over 25 to the power of 1/3. If we use again, if our FCU is 25, then we don't need to get these values. If our FCU is 25, then our allowable value for your shear should be 0.52. Okay, so that's why here it says that, okay, it's 0.55 allowable, 0.55, no, here 0.55 is your allowable, actual is 0.20, so it's fine. It's less greater, the allowable VC is greater than the actual, so meaning there is no requirement of stirrups, which is exactly correct, that because the slab doesn't have stirrups. Okay, in our calculation, slab doesn't need requirement for shear reinforcement. This is just to prove, to show with our calculation that there's no requirement with the shear reinforcement. Then after which you need to compute for the deflection. And the deflection, you just need to get the actual, okay, actual deflection span and then effective depth. Here better to use 7,000, okay, because it would be the critical one, the longest, okay, the longest span, okay. So you check this one. Now just do it with yourself. For example, our value is 33.3, okay. Now with the permissible, we just need to calculate, okay, this modification factor. We already know how to calculate modification factor since one-way slab, right? So we just have this formula, okay, this formula. This is Fs, whereas Fs, this formula also. A is required for your main bar, okay. This is 359. What we provide is 393. So that's why we have here 393. The one that we have provided, 359, is the one we required or calculated. Moment is the moment that we use for the critical side, which is the biggest one, 22.27. Okay, then you have your B is 1000, D is 150. Just substitute it here to get this modification factor of 1.39. You multiply it by 26. What is this 26? Because for continuous slab, it's, or two-way slab, it's always continuous, okay. For one-way slab, it is simply supported. So we use 26, and then you have 1.39, that becomes 36. So that means if this is your beam, this is your actual deflection, which is 33. Okay, this will be your, let us say, permissible, which is 36. Okay, so that's fine. Okay, and the permissible is 36, or the allowable is 36. Your actual is only 33, so it doesn't exceed the allowable value. If, for example, this actual is 40, so meaning it's over here, okay, so meaning it's bigger than the allowable value. So you need to increase the depth if it happened that your actual is bigger than the permissible. Okay, so after which you come up with this detail. Okay, you can just use this way of detailing. This is more easy to understand, but in British standard we are using this code. Okay, here it's easy to understand. So this would be the last part that you are going to present in your design procedure. So thank you. If you have question, just drop your question in the comment section.